In this presentation, we'll cover global navigation satellite systems and the global positioning system. We've got a lot to cover. This is a brief outline of some of the things we'll hit on. We'll also cover some other things not in this list, like common GPS file formats, as well as different applications of GPS and some of the newer things that GPS is being used for. We will definitely cover these things as well, a little bit about history and the segments of our GPS system here in the United States, almanac and ephemeris information, accuracy, sources of error, and some other things. So GNSS, Global Navigation Satellite Systems, and GPS are everywhere now. They are ubiquitous in our society in all parts of the world. What is this based on? Simply put, and I'm sure I don't have to tell you, it's based on your phone. Mobile devices now have embedded GPS chips in them. Because of these embedded GPS chips, you're being tracked at all times. Now, maybe you've turned your location services off, but even if you've turned all of your location services off and been very careful with your privacy settings, your cell phone company still has a record of where you go based on triangulation from cell phone towers. So be aware of that. Phone companies maintain location records, and they're often subpoenaed by law enforcement. It's similar to the old days when law enforcement officers would get a judge to write an order for a phone tap so they could get information about people. These days, law enforcement subpoenas location records from phone companies at incredible rates to try to better enforce laws in our country. So there's lots of records of where you go based on your phone. I'm curious how many of you have seen your Google location history. I'm going to bring up Google Maps here and give you a quick look at how to find out what your location history looks like. If you open Google Maps and you're logged in with your Google account, you can go to this drop down and you can go to your timeline. And if you go to your timeline, you'll see location history. And you can drill down based on years and months and days and find out lots of information about where you've been. You can also manage your location history down here. Now, I've had a lot of different phones over the years. Some have been Androids and some have been iPhones. And on some of my Android phones, I had the Google My Tracks location tracking app on my phone. So there's been times that my location history has been tied down more strictly than others. But you can dig down and really find information about where you've been in your Google location history. I encourage you to go look at that. So, lots of good things comes from GPS. Lots of bad things come from GPS. Some kind of fall in both of those containers. Navigation, for instance. We're all very lucky to be able to use GPS to find our way somewhere that we've never been before, or maybe even somewhere we've been before. And that's a great advantage of GPS. The downside of that is that as a society, people's spatial awareness, their ability to find their way around is diminishing over time because they're not working those parts of their brains. They don't have to do that. So navigation is a good thing that comes from GPS, but it's also kind of a mixed bag. Things like search and rescue are certainly positive things that have been enhanced based on GPS technologies. As a very recent, example, I've been seeing some articles where they're tracking COVID-19, and early on when the disease hit the United States, and there were a lot of people partying on beaches in Florida, they've been able to track these people who were in Florida and left Florida to go to all other parts of the country and world. And they've been able to really tell how that disease is spreading based on people's cell phone data. Um, so that's been a useful thing to be done with GPS data. We also use it for better planning of cities and transportation. I'll show you an example of Strava and how that's been used. I can actually pull that up here in just a few minutes. Also, things like live traffic. If you've ever looked at Google Maps and seen the green lines on the roads that indicate traffic's moving along, the orange meaning it's the yellow, and then orange, and then red, meaning where there's traffic, all that data is streamed from people's phones via GPS that tells the system how fast cars are moving down the road. So I did some kind of quick searching on some articles I've seen over time, and I thought you might be interested in seeing some of these. I encourage you to click on some and check them out. The New York Times has a couple of really good articles on how people are being tracked, and there's some companies out there that are collecting this data and selling it to other people for all kinds of purposes. Now, all of the data is anonymized, meaning that it's hard to pull out an individual person out of it. But that being said, if your GPS location is at your house from 6 p.m. at night till 6 p.m. in the day, you can kind of tell where someone lives based on where they spend most of their time. So there's all kinds of really interesting information, and I'll click on a couple of them just to show you what some of these look like. Every moment of every day, mobile phone apps collect detailed location. So if you read through this, you'll start to see how it knows where people spend most of their time, where their classroom is. They've got some really good apps or some really good articles based on this stuff, and the New York Times has a really good data and mapping group. This one shows all kinds of locations of people throughout the day based on time, and it's pretty interesting to read some of this stuff. This one shows a typical day at Grand Central Terminal in New York. So some different articles that are maybe worth reading. There's a couple of different ones in here. One person was riding his bike by a house about the time it was robbed, and so he was a suspect based on that. That's kind of scary. If you're familiar with Strava, Strava is a fitness app, and I use it a good bit, and I'm going to show you some more stuff about it later. But lots of people use Strava, and their exercise routines are made public. And I can't get to this. There it is. So a lot of military officers were using Strava to track their exercise. It does a really good job at the metrics of helping you know if you're doing better on the run than you did last time, or how your run or bike ride compares to other people who have run the same route or rode the same route. But terrorists and other adversaries of the United States were looking on Strava, and they were able to see where people were running within the walls of military bases to get a better feel for what was inside the military bases. What goes on behind those walls? What does it look like behind the walls? So that's another pretty interesting example. Um, Strava is really neat, and you can look at Strava. I'll show this is their heat map. You can pull up their heat map, and it shows everyone who's made their data public and what the most common routes are that people take. So this is Asheville. So these are people running and cycling. If you've ever been down to Carrier Park and the Melodrome down there, that's the Melodrome in Carrier Park. This is the Biltmore Estate, and here, I'm not sure exactly what that is there, but that is, oh, that's the Biltmore Estate too. Yes. So a lot of this is the Biltmore Estate. And then this is Bent Creek, where you can really see people ride their bikes a lot. And you can see the most common trails and roads that people utilize based on this heat map. So it's pretty interesting the amounts of data that are out there because of this. Speaking of Strava, speaking of the goods, the bads, the uglies of GPS data, Strava actually makes their data available to communities to better plan transportation routes. So they've got all this data indicating where people go and how they ride and how they move through a city. And so they allow people to use it, they sell it to try to help better plan cities. So other interesting applications there. This is kind of an old example that I like to that I've been showing for a long time. I know where your cat lives. When you take a picture with your phone, depending on your settings, the lat long of your location may be embedded in the metadata of the picture. This particular researcher pulled millions of photos of cats off of the internet that were freely shared, public facing on sites like Flickr. He just downloaded ones that he could get that were shared with the public, and any of them that had lat long turned on when the pictures were taken, he geocoded them and put them on the map. So this is pretty interesting to show. So the implication is, if you know where, I guess there were photos tagged with cat, is what they were. The implication is, all right, so some of those aren't the best examples. Well, let's see. Let's go to some kind of more of a neighborhood area. Here's a good one. The implication is if someone took a picture of their cat and inadvertently put it up and didn't even know lat long was tagged in it, the implication is, I know where you live, not just I know where your cat lives. So that's pretty interesting. I don't recognize that cat. I used to live right there. But anyway, okay. So just some interesting applications and some things to think about when we talk about GPS. All right, so a lot of people know what GPS is. A lot of people have heard of GPS. What about GNSS? GNSS is any satellite navigation system with global coverage. So GPS is the United States Global Positioning System. It is a GNSS. The term GNSS is used to refer to all satellite systems that have global coverage. As of 2016, the United States GPS system, actually termed Navstar GPS for Navigation Satellite Timing and Ranging GPS, and the Russian GLONASS were the two fully operational systems. The Navstar GPS has 32 satellites up there. To be considered fully operational, they say it needs 24. GLONASS has 28. So other countries are working to build their own. The EU is working on Galileo. China is building Budo. And India is building one as well. So it's a military strategic advantage to have your own GPS system. So though GPS is a subset of GNSS, receivers are differentiated as GPS, meaning they only can receive GPS signals from the Navstar United States GPS system or their GNSS. If a GPS receiver is only GPS, it only gets signals from Navstar. If your GPS receiver actually receives signals from the Russian system and the United States or others, it's referred to as a GNSS receiver and can have up to 60 satellites available for viewing. The more satellites you can receive location information from, the more chances of better accuracy. So our system, the Global Positioning System, uses at least 24 satellites. There are currently 32. It also needs a receiver and algorithms to provide location, velocity, time synchronization for air, sea, and land travel. When you hear GPS, we're typically talking about the United States navigation system known as Navstar or Navstar GPS. It should not be confused with GNSS, GLONASS, GPS receiver, or any of those things. The GPS system is owned, operated, and controlled by the United States Department of Defense. The history of it, well, it was made for military use. Throughout the 1960s, the Navy and the Air Force were working on a number of different systems to provide navigational capability for a variety of applications like monitoring troop movement and dropping bombs in really precise locations like through windows. In 1973, the Department of Defense directed that the services be unified. So the basis of this new system would be atomic clocks carried on satellites. The Air Force was chosen to operate the new system, and they called it the Navstar Global Positioning System. This new system called for three components: ground stations that controlled the system, a constellation of satellites in Earth orbit, and the receivers that were carried by users. The system was designed so that the receivers that the users use on Earth don't require atomic clocks. This allows the receivers to be small and to be made inexpensively. If the receivers had to have an atomic clock in them, no one would be able to afford one. I've seen that atomic clocks cost everywhere from $100,000 to $250,000. By 1978, the launch of the first Block 1 Navstar GPS satellites took place. They launched 4 satellites at that time. In 1983, the GPS system became available for civilians, but even then, the government controlled the signal and deliberately made GPS less accurate using something called selective availability. In real time, when selective availability was turned on, GPS was intentionally made, the accuracy of it was intentionally degraded to 100 meters or over 300 feet in real time. Now, the GPS in your phone can be as accurate as 10 feet. It's usually around 15 feet. It can be worse. So in the early 1990s, the GPS services were partitioned into the standard positioning service for the public and the precise positioning service for the military use. So there's still some difference in what the civilians use and the military use. In the year 2000, selective availability was discontinued. So, selective availability, the intentional degrading of the signal, is no longer on. The global positioning system reached a fully operational capability in 1995, meaning there were 24 satellites up there. And per U.S. policy and law, the GPS standard positioning service is available to civilian users worldwide for peaceful transportation, scientific, and other uses free of direct charges. So let's talk a little bit about the segments. We said it's based on these three segments: control, user, and the space. So the controller monitors the system and sends any adjustments if necessary. The Department of Defense operates this segment from Falcon Air Force Base in Colorado Springs, Colorado. There is an alternate master control station, 11 command and control antennas, and 16 monitoring sites. This map does a pretty good job of showing where most of these things are. You can learn a little more about the monitoring stations and the control stations. Space is the other segment. NavStar stands for Navigation, Satellite, Timing, and Ranging. We base the location of satellites and the distance from a satellite to a receiver based on timing and ranging. A fully operational system consists of 24 satellites. They're constantly being commissioned and decommissioned as they get old, as the newer block satellites come out. Not constantly, like daily, but they're constantly being upgraded. They have very high orbits above Earth, around 10,000 miles or 20,000 kilometers. They have a revolution about every 12 hours. If you've ever seen a representation that shows satellites that are orbiting the Earth, there are a tremendous amount of them very close to the Earth. Those are all the communication satellites. The GPS satellites, by design, have very high orbits where the math to model their orbits is simple and there's less to interfere with their orbits, giving them a nice smooth orbit. And then you've got the user, or you should say maybe the receiver. So there's lots of types of receivers these days. I used to just have a picture of a Garmin GPS unit like the one in the top center. We think of those as consumer or recreation grade GPS units. The one farthest to the left is one that like a surveyor may use. It's a much higher accuracy, much more expensive. The one on the farthest left probably costs $25,000 and it can get an accuracy of sub-centimeter. That Garmin in the top middle probably costs $250 and can get an accuracy of down to 9 or 10 feet. The top right corner is a Bluetooth GPS unit that connects to an app on your phone that we'll talk about when we get to the Esri world of GPS apps for your phones. You can connect a Bluetooth GPS receiver like that to your phone wirelessly and get your GPS accuracy down to a foot or less. Then you've got GPS antennas in phones and on watches. I put that middle one on the bottom that's yellow in there because that's what I was using in the mid-90s when I first started using GPS a lot. It got down to sub-meter accuracy for about $10,000. So all of these are different examples of GPS receivers, and there's many, many more, of course. All right, so the GPS receivers on the ground, or what we think of as what the users use. These days, civilian users outnumber the military by a lot. There's many applications. I mean, I can't even start to list them all. Emergency services, public safety, recreation, asset management, keeping up with manholes and fire hydrants, routing, precision agriculture, vehicle tracking, and I just put tracking disease in there, not that it's new, But with all that's going on with COVID-19 right now, there's a lot of people trying to better understand the disease by looking at how it spreads, and phones are a good way to do that. So why do we use satellites? With satellites, an accurate position can be determined without having a direct line of sight between the known and the unknown location. You do need a clear view of the sky. You can determine an accurate position almost anywhere on Earth at any time by using satellites. GPS does not work indoors, and GPS does not work well right up against a building. And we'll talk more about that when we talk about error. So how GPS works is based on satellite ranging. We said NavStar stands for Navigation, Satellite Timing, and Ranging. Satellite ranging is the measurement. This measurement is determined by timing how long it takes the radio signal to go from the satellite to the GPS receiver. And we use that time to calculate the distance that one satellite is away. Okay, so we use satellite ranging to determine the distance a satellite is from a receiver. Two factors are involved in measuring the distance. We know that the speed of the radio signal is the speed of light, 186,000 miles per second, and then we can determine the time it takes the signal to reach the receiver. So if you take the time multiplied by the speed, you can get the distance. So we know that the time a radio signal traveling from the satellite to a receiver is very fast, the speed of light. It takes a few thousandths of a second for the signal to go from a satellite that's directly overhead to the receiver. So since the satellite has an atomic clock in it, timing is very precise there, but the receiver does not have an atomic clock. So how in the world do we figure this out if the two don't both have very precise clocks? They use a pretty neat trick. Each GPS satellite and the receivers transmits data that's actually a pseudo-random code that indicates its location and the current time. All GPS satellites synchronize operations so that these repeating signals are transmitted at the same instant. The distance to the GPS satellites can be determined by estimating the amount of time it takes to go between the two, right? So this is what happens. That signal is actually called a pseudo-random code because it looks random, but it's not. So if the exact same code leaves the satellite and the receiver at the same time, when they get there, there's a slight offset in the two. And if you shift the two back until they match, you can get the timing offset to sync the times between the clocks. So the analogy that you often hear is that if you were standing on Earth with your GPS unit and your satellite's way away from you, and if the Star-Spangled Banner or any song started playing at the exact same time, you would hear the Star-Spangled Banner coming out of the receiver immediately, but it would take it a while to get to you from the satellite, and so you start hearing it slightly after, and so there'd be this little delay in the two you're hearing. And so if you could shift those two together based on the time it took the sound to reach you to start hearing the song from the satellite, that's where you get that timing offset. So it's a pretty neat trick that allows you not to need an atomic clock in the receiver. So that's how you find position to one satellite. To get a location, we use a concept similar to triangulation. In trigonometry requires 3 perfect measurements to define a point in 3-dimensional space. With the GPS position, we call it trilateration because there's no angles in space. It is measuring of the distance from at least 3 satellites to establish a position on Earth. So the accuracy of a measurement based on 3 satellites is diminished due to the synchronization of clocks in the GPS satellites and receivers. So we use a 4th satellite to eliminate the timing offsets. So with trigonometry, you need 3 perfect measurements. We don't have 3 perfect measurements, so we use a 4th satellite. The microprocessor in the GPS receiver recognizes the timing offset when it receives a series of measurements that it can't intersect at one point. Then it automatically starts subtracting the same amount of time from all the measurements until one point is determined. So, the question of how many GPS satellites do you need to be tracking to get an accurate measurement, a really accurate measurement? You need 4. So you can think of it like this. If you are getting a GPS signal from one satellite, you could be anywhere on the sphere. It doesn't know where on that sphere you are. When you add in a second satellite, you are somewhere in the intersection of the 2 spheres. The third tells you you're at one of these 2 points, and the 4th helps throw out the other one as a ridiculous answer and determine your location. So there's a couple of different sets of information you need to be aware of. The almanac information is a set of parameters used to calculate the general location of each satellite. So the almanac is used to do things like plan the best time of day to be out GPSing when you know how you have the best coverage of satellites. It's also used for when you turn on a GPS unit. If it's got a current almanac in it, like less than 30 days old, it knows where to scan for what satellites. So it acquires satellites a lot quicker. If you were to fly to India, get in a plane and fly to India and get out of the plane and turn on a GPS unit, it would take a while for the GPS unit to find and acquire the satellites because the almanac in it is looking for satellites that are based on where you were last time it got a current almanac. Now, the GPS unit gets an updated almanac from the satellites anytime it connects to one. So if you're GPSing a lot, you've got a current almanac. If you turn your GPS off for 6 months and then turn it back on, you don't have a current almanac. You could download a current almanac for a given location and put it in a GPS unit, but I typically find it finds them quick enough and gets a new almanac as quick as you could remember how to find the almanac and download it and put it in. With your phones, of course, they've almost always got an updated almanac because you're always using your phones. So the almanac information, general information for where all the satellites were. If you looked at the GPS for mobile apps video in this module of work, the GPS plan app that shows you where all those satellites are, and when we scanned through it to show where they would be at different parts of the day, it was because of the almanac knew where it would be. You can also go to websites like this GNSS mission planning site, and you can begin planning. And if you put in a place like Asheville, let's see if it finds it with that. Yeah, okay. And I apply it. And I could put in whether or not I'm working in an urban canyon or in a natural canyon. Shows you your satellite libraries, settings, charts. Let's see. Okay, so these charts show in Asheville the number of satellites from at different parts of the day for different systems, the elevation, where they are. So it's a little bit slow. Where they are in the sky, essentially. You don't want satellites to be low on the horizon because they go through, the signals go through more of the atmosphere, which introduces error. We'll get to that. Here's the sky plot. Shows you where they are. And if you play this, it shows you where they are throughout the day. How does it know where they are throughout the day? By looking at the almanac. It keeps up with the location of satellites. So these mission planning sites, if you're doing very high accuracy GPS, like survey grade GPS, you need to track the same set of satellites for a long amount of time, and there's some pretty precise requirements for getting data that's like sub-centimeter grade accuracy. And so planning the best time to be out in the day when you know you have the best geometry of your satellites, which has to do with the dilution of precisions. The PDOP is the positional dilution of precision, and it's a measurement of the geometry of the satellites in the sky. So you want to be out there when you've got satellites spread out in all quadrants of the sky. You want to have at least 4 satellites. More is better. But if they're all in one quadrant of the sky, it doesn't triangulate as well. So these mission planning softwares help you to plan the best time to be out there if you're doing high accuracy GPS. If you're going for a bike ride and you want to track your ride, you don't worry about any of this. This is for high accuracy survey grade GPS, which is beyond the scope of most GPS or GIS applications anyway. All right, so then there is the ephemeris information. So the almanac is the general information locating that tells you where all the satellites are. The ephemeris is the specific information, the exact location on one satellite. So the orbits of all GPS satellites are measured constantly by the DoD. They determine satellite ranging, and they calculate that exact location of each satellite. If you're going to use satellites to triangulate an unknown position on Earth, you have to know their exact positions. So they keep up with exactly where they are. They send adjusted measurements to the satellites to keep them right in orbit. The minor corrections are transmitted by the satellites back as ephemeris information. The ephemeris information is a data file that contains the orbit information for one particular satellite. It's used along with it's used by the GPS receivers along with their internal almanac to establish a precise location of a satellite. So the almanac and ephemeris information are both very important. They serve similar, sometimes overlapping, and sometimes different purposes. So how about accuracy? GPS accuracy ranges greatly. Autonomous GPS, GPS that has had no error correction applied to it, is plus or minus 10 meters at best, so 30 feet off or more. That's autonomous GPS. There's not a lot of autonomous GPS around anymore. Almost all GPS has some kind of differential correction applied to it. That's differential GPS. Differential GPS ranges from sub-centimeter survey grade to a few meters, 10 feet, 15 feet, which we refer to as mapping grade. That depends on the type of correction, the type of GPS signal, carrier or code phase. Carrier is much more accurate than code. The GPS antenna you have, how much data you collect, and other factors. So what is differential GPS? It's the precise measurement of the relative positions of two receivers tracking the same GPS signals. One receiver is placed at a base station over a known coordinate. So you've got a GPS receiver sitting over a known coordinate, looking at the exact same satellites that your receiver that's in your phone or in your GPS unit is looking at. And the receiver that you're walking around with is referred to as the rover. It's in an unknown location. But the other receiver's on top of a known coordinate. And so it can look at the signals it's getting and determine the accuracy based on its known location. Then it can apply that error correction to the roving unit as an error correction. So there's lots of ways differential GPS is done. In professional applications for mapping and surveying, surveyors sometimes set up their own base station to get corrections in real time. You can even do it through cell phone data links to the National Geodetic Survey. The National Geodetic Survey also sets up CORS base stations all over the place, continuously operating reference stations. All of those are for professional grade GPS units. Your phones and your more consumer grade Garmin GPS units and things like that, they use a system called WAS. It's a type of differential GPS. Excuse the typo. It is a type of differential GPS, and it was developed and implemented by the FAA. It's a Federal Aviation Administration system. They've got approximately 25 ground reference stations. They cover a large area. The signals from GPS satellites are received by these wide area ground reference stations. Each of these are precisely surveyed so that we know the exact location. So what happens is there's two geostationary satellites that never move, one over the Atlantic Ocean, one over the Pacific Ocean. They've got these known reference stations. They transmit the correction up to a satellite, and then it comes back down to your phone or your GPS unit. So WAS increases GPS to better than 3 meters or around 3 meters. So this type of differential GPS is not as, doesn't give you the accuracy of some others, but it does make GPS for the masses for free, for really inexpensive GPS units, much more accurate, down to 12 or 15 feet easily. So WAS is on most consumer grade GPS units that are not the expensive professional grade. So how about accuracy? The accuracy of a GPS position is determined by the sum of several sources of error. Selective availability used to be a big one. Obstructions that cause multipath cause error. Okay, so if you're looking for satellite ranging, how long it takes the satellite signal to go from a GPS unit to your receiver, if it doesn't go in a straight line, if it bounces off of a building, or if it bounces through a bunch of leaves on the way down, that introduces error. Okay, so obstructions and multipath introduce error. If you stand right up against a building and try to GPS a sidewalk, and you're blocking half of the sky, and the signals you are getting are bouncing off the building, then it's going to be much less accurate. Also, atmospheric delay. That's actually the biggest source of error. The signals travel through the ionosphere and the troposphere. The ionosphere is the higher part of the atmosphere that is all electrically charged, and so the signals bounce through that, and then they bounce through the troposphere, and you get a lot of error from that. Some of it can be modeled out in real time. Now, your error, as you look at it, it's constantly changing. I mean constantly changing. Not tremendous amounts, you hope, but just little bits. 15 feet, 16 feet, 20 feet, 14 feet. GPS does work in all weather conditions. All right, so original system, the government imposed that accuracy degradation to 100 meters. Why? I'd first started teaching GPS right about a couple years before it got turned off, and I was using it before. In real time, you'd go out in GPS, and you had to differentially correct it to get something that looked anything like the parking lot that you GPSed. They did that because they didn't want someone to be able to use the GPS system to hit the White House with a missile. And lo and behold, turns out that's what we use it for. Even the 9/11 World Trade Center terrorist, they had $100 Garmin GPS units in those planes that flew off from Philadelphia with the lat long of the World Trade Center in it. And they just turned those things and pointed them straight towards a coordinate hundreds of miles away they couldn't see. So there's so much civilian use from engineering to farming that they turned it off. Now, autonomous GPS, like we said, is over 30 feet. And then there's a bunch of different types of differential correction depending on the hardware, the GPS unit, the how much you pay, and the bands you use. And it's getting better all the time. Applications, just tons of them. Okay, drones, environmental analysis, games, the Pokemon game, tracking people, people on house arrest, and of course the spread of disease. So professional grade versus consumer grade, what's the difference in some of these things? So a professional grade GPS unit can cost many thousands of dollars. I mean, a few thousand to 15 to 20,000. Okay? And then you think, well, God, Garmin only cost a couple $100. Is there that much difference? There's a good bit of difference. With some of the professional grade GPS units, you're able to establish what they call rigorous data collection parameters. You're able to set these settings that ensures you're only getting the best data. So if you don't have a good geometry of satellites in the sky, if your positional dilution of precision is not over a certain threshold, it says, don't collect data. I can't get accurate enough because all my satellites are in one quadrant of the sky. If the signal strength, the signal noise ratio, if the signal strength's not good enough, the professional guys will just say, stop collecting data until it gets better. Okay? Also, elevation mask, normally less than 30 degrees, not greater than, less than 30 degrees. 30 degrees is the highest you would have. Also, number of satellites, you can say, if I don't have 5 satellites, I'm not collecting data. And you can even put in that you want a minimum number of positions on point features so you can average them. You could sit on a manhole and you could collect positions for 5 minutes and then average hundreds of positions together, which gets you more accurate data. Usually you put in a minimum number of positions of like 3. So you're able to have these settings that automatically filter out a bunch of data. All right. Now, that's one thing they do. They also allow you to work with a comprehensive suite of software that assists with setting up your project, doing mission planning, differentially correcting your data, exporting to GIS. Also, if you're out doing a project where you're going to be going to a campus and you're going to be collecting data for like a month, you come in and you download your files into the software and it automatically stores them in a directory structure, and then you can combine the files from day to day. And a big thing you can do that I didn't put in here is that you can build a database schema. for data collection. So let's compare these things that I just mentioned with, and think about what you do with a Garmin GPS unit. So when you go with the Garmin GPS unit or your phone, it's collecting all the data that comes to it. It doesn't care if the PDOP's bad. It doesn't care if satellites are below an elevation mask. It doesn't care if the signal strength is low. You're getting all that data, good or bad. Also, when you go to GPS, and this I should have mentioned early on, as GIS professionals, you should think of GPS as a tool to create thematic GIS layers for a GIS. I mean, sure, I use GPS several times a week to track a run or a ride, but as a GIS professional, I use GIS to build GIS databases. And GIS databases typically have comprehensive attributes through a database structure or schema. So with a Garmin GPS unit or one of these apps on your phones like Gaia, you could go GPS all the trees on campus, but you couldn't build out a database that had the tree name and the tree height and the tree condition and the diameter at breast height and whether it's a conifer or deciduous, all these things you want to collect for a GIS, all this attribute information. Professional grade GPS units have software and systems that allow you to do all of that. This shows how you can control that error and those settings in a Trimble GPS unit. Those are professional grade units. You can control the maximum PDOP, the minimum signal strength, the elevation mask, and all that stuff. And the Trimble software that you would use for that are Pathfinder Office on the desktop, and TerraSync is on the field data collection software, should you see Trimble in the workplace when you get out there. Esri has options for those softwares as well. GPS Analyst takes the place for Pathfinder Office, and you use ArcPad on the actual GPS unit instead of TerraSync. There's a bunch of newer Esri apps that integrate with a phone and ArcGIS Online. We'll be seeing Collector for ArcGIS this semester. We widely use it now in our classes. It allows you to do many of those professional grade GPS things like build a database for data collection and make a workflow for working out in the field many days in a row. The one thing it doesn't do when you use it on a phone is provide high grade accuracy. The workflow and procedurally it's all the same. You would need a Bluetooth GPS unit that costs about $2,500 to get professional grade GPS. So we're not able to do that in our class, get the high accuracy GPS data using Collector, but we are able to understand and utilize the entire workflow from planning your GPS project to building out your database to pushing the GPS structure to ArcGIS Online to collect data into. We're able to do the whole workflow just with not quite the accuracy. How about all the other apps? Hundreds, thousands actually of apps for download, free or paid, that allow you to capture GPS information. So we use Gaia GPS just to introduce it. These typically allow export to GPX and KML. They must be converted to a shapefile or geodatabase feature class for viewing in the Esri world. So all these other apps allow you to create and collect GPS data for free. That's awesome. Those file formats don't work in the Esri world, so there are some different utilities for converting them to the Esri formats, and we'll see some of these. Most of these apps don't support higher accuracy GPS antennas. They don't support the database creation for capturing many attributes or the professional workflows for supporting multi-day projects. A quick word on file formats. Again, the common open data formats, GPX and KML. Those you'll see in the mobile apps for phones. In the Trimble world, the SSF is the uncorrected rover file. Once you differentially correct it, you get a COR file, and then you can export it to an Esri format. And then with the apps, the collector app and integrating with ArcGIS Online, those apps within the Esri world just collect data directly into their formats. All right, if you have any questions, please don't hesitate to contact me.